Today we cover section 12.3 and in doing so introduce the idea of probability. So what is probability? I want to introduce it through an example. Suppose we take a standard die, sides 1 through 6, and we want to know the probability that the number rolled is less than 5. So what do we need to know in order to answer this question? First of all, we need to know what we mean by probability. We have to be precise. And for us, the probability of event E, which we write P of E, is a real number between 0 and 1. And if the probability comes out to be 1, that means the event is certain to occur. If the probability comes out to be 0 for the event, that means that event is impossible. So for an event E, the probability of E is the number of equally likely ways E can happen divided by the total number of possible equally likely outcomes. In other words, when you're looking at the probability of something happen, you count the number of ways it can happen and divide by the number of ways anything could happen. So what are the equally likely outcomes here? Well, think about it. You're rolling a standard die, so your possibilities are 1, 2, 3, 4, 5, or 6. How many of those are there? Well, obviously there are 6 of them. How many of those, though, are less than 5? Because remember, we're looking for the probability that the number is less than 5 when we roll the die. Well, 1, 2, 3, or 4, those would all be less than 5, and there are 4 of them. So there are 4 results less than 5, and there are 6 total possible outcomes. So by the definition, the probability of rolling less than a 5 is the number of ways you can roll less than 5, which we decided was 4, divided by the number of ways you could get anything, which of course is 6. And 4/6 obviously reduces to 2/3. So the probability, if you roll a fair die, that the roll comes out less than 5 is 2/3. That's sort of our first introduction to the idea of probability. The set of all possible outcomes is called the sample space. The sample space is a set of anything that could possibly happen when you roll a single die. Speaking informally, we might say the probability is just the likelihood of an event happening. We're going to talk about 2 different types of probability. The first is called classical. That's based on theory, and we're generally going to count the number of ways an equally likely event can occur and divide by the number of elements in the sample space, basically, which is what we did for the previous problem. That's classical. The other type is empirical, and we'll get to some of those later, but that's based on observed results. It's not necessarily theoretical. You observed what's happened in the past and base your probabilities on that. And if you're using empirical probability, you have to define the probability slightly different, but notice it's not very much different. The idea is the same. In an empirical sense, the probability of an event E is the number of equally likely ways E occurred. In other words, we looked at what happened in the past, divided by the total number of equally likely outcomes possible. So we're looking back to history and getting those numbers instead of basing it on theory. But the idea is the same in either case. And also remember that the probability of an event is always between 0 and 1. If the probability is 1, it means it's going to occur for certain. If it's 0, it means it's impossible and can never occur. Another example. A standard die is rolled. Find the probability that the number rolled is greater than 2. We approach it in exactly the same way as the previous problem. The probability of that event E happening is the number of equally likely ways that E can happen divided by the total number of possible equally likely outcomes. Well, we're looking for the probability that the die roll comes out greater than 2. So you got to look at the sample space. We've talked about this before. The sample space is a set containing 1, 2, 3, 4, 5, and 6. So we want the number of equally likely ways you can get greater than 2 in the numerator, and that will be 3, 4, 5, or 6. That's 4 things, divided by the entire size of the sample space, which is 6. And 4/6 reduces to 2/3. Very similar to the previous problem. In fact, so similar that the answer is the same, but that's just coincidental. Some probability problems will refer to experiments that involve rolling two dice, not just a single die. So we need to spend some time talking about those. In particular, I want to show you the sample space for that. Remember we talked about two-stage experiments earlier and said that when there's a two-stage experiment, a table is often a good way to handle it, and that's true here. So if I'm rolling two die, I'm going to make a row for die 1 rows. For die 1, you could get a 1, 2, 3, 4, 5, or 6, and then I'm going to do column headings for die 2 row, which again you could get 1, 2, 3, 4, 5, 6. So the row labels represent the possible die roll for die 1, and the column headings represent the possible die rolls for die 2. And if you look at the intersection of those, you get every way you could roll two die and get some combination of numbers 1 through 6. And as you can see, the interior of that table is 6 by 6, so there are actually 36 elements. So that means that the sample space has 36 elements, and if the die are fair, those are equally likely results. I will note that in the book and in the software, sometimes they give you a different visualization of that die roll. I don't particularly like to see it that way because I think doing it in a table is actually easier. But if they give it to you, you certainly want to be able to use it. So just keep in mind that I prefer the table on the left, but sometimes you'll see the visualization that they've given you on the right, and you can work with that as well, and I'll show you both ways. Let's take this example. Two regular six-sided dice are tossed. Compute the probability that the sum of the pips, those little dots are called pips, compute the probability that the sum of the pips on the upward faces of the two dice is, and we'll do a couple of variations. Let's say first of all 8. Now if they give you that visualization that I mentioned earlier, then just look at it and look for the sum of 8. For instance, I'll notice that 2, 6 is 8. If you just search around for any combination of 2 that add up to 8, that 3, 5 is equal to 8, 4, 4 is equal to 8, 5, 3 is equal to 8, 6, 2 is equal to 8. And if you search through that entire visualization, those are the only 1, 2, 3, 4, 5. Those are the only 5 that give you a sum of 8. So going back to the definition, the probability that the sum is 8 is the number of ways you can get 8 divided by the number of elements in the sample space. In other words, what could possibly happen? Well, as we've already observed, there are 5 different possibilities that give you a sum of 8. So the numerator is 5, and the denominator is just the size of the sample space. The size of the sample space is 36. That just reflects the fact that there are 36 possible things that could happen when you roll two dice. So the probability that you roll a sum of 8 when you're rolling two dice is 5/36. Now let's answer a different question. What is the probability that you roll at least a 9? Well, at least 9 means you either get 9, 10, 11, or 12. 12 is the biggest possible sum you can get because that's 6 and 6. Again, the probability calculation is the same. So we just have to count the die rolls that give you at least a 9. So let's start off with 9. Well, 6 and 3 give you 9. 5 and 4 give you 9. There's another 5 and 4, but it's a different pair of dice. There's a 6 and 3. That's exactly 9. Then you move up to 10. Well, there's a 6, 4. There's a 5, 5. There's a 4, 6. Then you go to 11. There's a 5, 6. There's a 6, 5. And then finally there is a 6, 6, which gives you a sum of 12. Those are the only possibilities that give you a sum of at least 9. And if you count them, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of them. So the probability would be 10 over 36, which is the entire sample space size. Once you understand the basic principle, the process is straightforward. You can reduce 10/36 to 5/18 if you like. I mentioned you can use the tables as well. If they give you that visualization, you probably should just go ahead and use it. But if you had done tables for this, you'd get the same answer. You'd still find out for both of those problems that you could have gotten 536 and 1036 by using the tables instead of that other visualization. But if they give it to you, I would say use it rather than taking the time to actually build it into a table instead. I told you last time that we'll be using decks of cards a lot for our problems, and this is a continuation of that fact. Suppose we have a card selected at random from a standard deck of playing cards, and we want to find the probability that the card is a face card. Remember, we talked about this last time, that face cards are the jacks, queens, and kings, the things that actually have faces on them. And there are 12 of them. So the probability that the card is a face card is the number of face cards divided by the total number of cards. Well, the number of face cards is 12. The total number of cards is 52, so we get 12 52nds. If you reduce that, it becomes 3 13ths. So the probability of drawing a face card out of a well-shuffled deck of cards is 3 13ths. This problem says, use the data in the table to compute the probability that a randomly chosen voter from the survey is between 39 and 49 and is a registered independent, and then round your final answer to the nearest hundred. So we keep our answers as fractions unless they tell us to round something. And as soon as they tell us to round something, we know we can use decimal approximations. So the probability that the person is between 39 and 49 and is an independent is what we're looking for. So that's going to be the number of people who are 39 to 49 and independent over the total number of people altogether, in this case the voters, which is given in the table. So if we're looking at that, the numerator is the number who are 39 to 49 and independent. So if you look at the number who are 39 to 49 independent, you first start with the 39 to 49, that row, and then you look at the independent column, and the ones that are both, and means intersection, are the 150 that are in both the 39 49 row and the independent column. So the numerator is 150, and the denominator is everybody, which are all the voters, and as the chart tells you, that's 3,228. And since they ask us to round the answer to the nearest hundred, that gives us permission to use the calculator instead of just reducing the fraction. And if you do that and rounds it to the nearest 100th, you'll find out the answer is 0.05. In other words, there's a 5% chance of that happening if you just pick a voter out of this group at random. This is an application to genetics, and actually it's pretty interesting. If you study any biology, you probably know a lot about this already. The Human Genome Project, which was actually completed back in 2003, was a 13-year-long project that was designed to completely map the genetic makeup of Homo sapiens. The concept goes way back before that, though. It began with Mendel and his work with flower color and how it was transmitted from generation to generation. Mendel found out that the flower color followed a certain pattern that could be predicted by making certain assumptions about what caused a plant to have a certain colored flower. And what he found was that red was a dominant determiner and that white was a recessive determiner. And in today's language, you would talk about a gene for flower color and the allele of the gene. In any case, a gene consists of two dominant alleles, which means two reds, a dominant and a recessive allele, a red and a white, or two recessives, which would be two whites. So each gene can be red, or a mixture of one red, one white, or it could be two whites. And because red is dominant, a flower will be white only if you don't get any red allele at all. The standard way to deal with this is a Punnett square, and if you've taken any biology, you already know about this, but I'll show you again. We're going to use, for us, a capital letter for the dominant allele, and then we're going to make a small letter to indicate whatever the recessive was. So in this case, we're going to use capital R, that's where you have red, and we're going to use capital R, little r for the case where one is red and one is white. So the little r is actually like the white. It's whatever the recessive is, in this case it's a white. Or you could get two recessives, which is little r, little r. So capital R, capital R, capital R, or little r, little r. Those are the possibilities, with the capital letters being the dominant, in this case red, and the small letters standing for the recessive, which in this case is the white color. So the Punnett square looks something like this. And this is an example of a Punnett square for a parent that has one red and one white allele and another one that has two white alleles. And to form the Punnett square, you just look at all the intersections. You take the capital R and pair it with the little r of the other parent, and that gives you a capital R, little r. Then you move over or down, whichever direction you'd like to work. In this case, I went down. And you pair the capital R with one parent with the little r of the other parent, and you get a capital R, little r. And then you keep going. You take the little r of one parent, match it with the little r of the other parent, and you get little r, little r. And then the same thing happens for the fourth cell of the table. Little r gets matched with little r. And so that gives you your Punnett square. That also lets you calculate your probabilities because that represents recessive and there are no dominant alleles at all. That would be the white flower. And the rest of them would be red. If there's any dominant in there at all, it turns the dominant color, which in this case is red. So as you can see, half of them are white and half of them are red. So if you wanted to look, you could say that a flower is red 2 out of 4 times, or half the time, and a flower would be white 2 out of 4 times, which is a half. In this particular set of parents, it would be 50-50. It'd be half and a half as to whether the flower that results from that mating would be red or white. It's true for that particular pairing of parents. How about this? A child will have cystic fibrosis if the child inherits a recessive gene from both parents. If we use capital F for the normal allele, which is dominant, and little f for the recessive allele, which is recessive, of course, suppose a parent who is capital F, little f, and again, that mixture of a capital with a little letter is, that person is said to be, or in this case it's a person, is said to be a carrier. And a parent who is capital F, there is no recessive allele there at all. If we want to do a Punnett square for those to decide what the probabilities are for the child, I can ask any number of questions, but let's start out with this one. What is the probability that the child will have cystic fibrosis? Remember, it has to be little f in order to have cystic fibrosis because the normal is the dominant. So if you make a Punnett square, you'll see that when you cross everything, you get a capital F, another capital F, and then you get a capital little. So there aren't any little f, so that means since you have to have little f to have the disease, you can see that no child of those two parents will ever have cystic fibrosis. That probability would be 0. And that's simply because there are no little f combinations. I could ask something else. For instance, what is the probability the child will be a carrier? Remember, a carrier is if you have one dominant and one recessive, so a capital and a little f. So if you look through there, there are 2 of them, and that's 2 out of 4. So that probability is 1/2. So the probability the child will have the condition is 0, but the probability that the child will be a carrier of the condition is 1/2. Now I want to talk about something that's related to probability, but looking at it in a different way, and that is the idea of odds. You probably already know a little bit about odds, but odds are just another way of expressing the same thing that probability expresses. And I hope that going through these examples I can show you that. When we talk about odds, we're also talking about probabilities. It's just different terminology and slightly different way of looking at it. An online story published on October 20th, 2014, referencing the Vegas Superbook odds board, reportedly had Alabama and Ole Miss tied for the team most likely to win the 2015 college football playoff with odds of 5-1 against. which we often write 5:1 against. Turns out that neither of them won it that year, but nevertheless. But what does that actually mean? One way to think about it, and the way I like to think about it, is to think of these numbers as being associated with slips of paper. In other words, if it's 5:1 against, it'd be like having 5 slips of paper that say no or not, and 1 that says yes or that you do win. So you have 5 negatives and 1 positive. So you have 6 slips of paper altogether. That's the way I think about it. If you think about it that way, this all flows so smoothly. 5 negative slips and 1 positive slip. Just again about this terminology, when I say 5:1 against, you can turn it around and say that would be 1-5 in favor. In other words, if you say against, the first number is the against number, but if you want to turn it around and say in favor of, the first number has to flip and the in favor of number has to go first. Saying that the odds are 5:1 against something is the same thing as saying that the odds are 1-5 for that thing. I want to take another minute to make sure you understand that notation, because if you don't, you have no hope of getting through this. If we say the odds of an event are A to B against, that first number is the against number. So in this case, the A would be the against number. But if I say the odds are A to B in favor of that event, then A is the in favor of number. Just the same as when I did the 1-5 versus the 5:1 example earlier. So going back to that example, it's 5:1 against. The against number is first, the in favor of number is second. But if I want to change it to in favor of, I would write it 1-5, and the first number would be the in favor of number, and the second number would be the against number. It's crucial that you understand that distinction. Anyway, back to the problem. If the odds against Alabama winning the 2015 college football playoff are 5:1, what is the probability that Alabama wins that? So I want to take the odds way of looking at things and change it back to a probability and show you that you can go back and forth between these two things. Well, here's how you do it. By what I call the basic probability principle, that's writing this thing as a fraction. I'm going to call that the basic probability principle. By the basic probability principle, the probability that UA wins this thing, that being the 2015 college football playoff, would be the number of slips up there that say win over the total number of slips up there. In other words, I've got 5 slips that say not win, that is, versus 1 slip that says Alabama does win. So to do the probability, you've got to count the winning slips over the total number of slips. Well, there's only 1 winning slip, but there are 6 slips altogether. So the probability that UA wins it is 1/6. The odds against them winning it is 5:1. The odds in favor of them winning it is 1-5, but the probability of them winning it is 1/6. I hope this discussion makes it absolutely clear just how closely probabilities and odds are related. You can freely go between those two things. You can say things in terms of probabilities. You can say things in terms of odds. One thing can be directly connected to the other. And here's how it actually works. If the odds against an event E are A to B, the odds against the event E are A to B, which would be the same thing as saying the odds in favor are B to A, then you can change those odds to probabilities by taking the probability of E as B over A plus B, remembering that B is the number in favor of, and A is the other one. So the numerator has the in favor of number, and the denominator has the sum of the in favor of and against number. So if you know the in favor of number and you're given a probability, you can figure out what the against number is by subtraction. For example, going back to our example with the Superbook odds, we found out that the probability that UA wins the national championship in 2015 is 1/6. If I go back and configure it in terms of the fraction just above, that means I've got to break 6 into 5 plus 1, because if I've got a 1 up top, that 1 has to appear in the bottom, and if I put a 1 down bottom, it takes a 5 added to that 1 to make 6. Well, once you do that, you can see that B is 1 and A is 5. B is the number up top, which also appears down bottom. The other number is A, so A is 5. So the odds against Alabama winning would be A to B. So that would be 5-1, which is what we know it is, because we started off with the odds against UA winning as being 5-1, and then we turned it into a probability of 1/6, and now I'm backing it up and taking the probability of winning being 1/6 and going backwards and changing it to the odds against winning, which is 5-1. Or I could also say the probability in favor of UA winning would be 1-5. So once you know odds, you can quickly change it to probability. If you know probability, you can change it quickly to odds. Finally, you can also relate probability and odds with this result. It says if you're given the probability of E, the odds against E is the probability that E does not occur, that's E complement, over the probability of E. Usually you write odds with a colon, so you could write that fraction, the probability of E complement over probability of E, as the probability of E complement colon the probability of E. That's a more common way to write the odds. Just a quick example. If I told you the probability of E is 0.3, then the probability of E complement would be 1 minus 0.3, which is 0.7, and according to this result, the odds against E is the probability of E complement over the probability of E. That would be 0.7 over 0.3. If you multiply the top and the bottom by 10, you can write that as 7/3, or 7:3. Now the fact of the matter is, this result is certainly true, but you seldom, if ever, really have to use this formula. If you like it and think it's cute and easy to use, you're welcome to use it, but there's really nowhere that you have to use that formula. You can do it some other way. But I threw it out there because in certain cases it is faster. Let's do another problem. A snack-sized bag of M&Ms contains 10 red, 5 blue, 11 brown, 5 orange, and 8 green. If a single piece of candy is randomly picked from the bag, compute the odds of getting a green. When you're looking at these problems, you also want to think about what they're asking as you read the problem. We're going for the odds of getting a green. We know that you've got a bunch of different colors, but you're really only interested in whether something's green or not. If you add all these up, you see there are 39 in all. You're only interested in green and not green, so I wouldn't worry about the 10, the 5, the 11, and the 5 separately. Just think of them as 31 things that are not green. So because the problem asks about the odds of getting a green, you merge all the non-green colors into one count. So there are 31 non-green M&Ms and there are 8 green M&Ms. So the odds of getting a green will be 8-31. The odds against getting a green, of course, would be 31-8. But we were asked for the odds of getting a green. Once you understand the principle, it's easy to do these problems. And again, odds, sometimes you use the word 2, 8-31. Quite often you use a colon, 8:31. You could actually write it as a fraction, just like you do a probability, 8/31. Those are all ways that odds can be written. Another question, what is the probability of getting a green? Okay, we answered the question about the odds of getting a green. What about the probability of getting a green? You could start over and just forget about the first question. The probability of getting a green is just the number of greens over the number of M&Ms in the bag. So you have 8 greens, you have 39 M&Ms in the bag, so the probability would be 8/39. What are the odds against rolling a 7 when rolling 2 6-sided dice? remember when you have two six-sided dice, it makes sense to make a table of these values. If they don't give you that visualization, you probably want to make a table. And we've talked about that before. So build that table and you get 36 possibilities. We're looking at the odds against rolling a 7. So you got to look in that chart and find your 7s. Well, 6 and 1 is 7, 5 and 2 is 7, 4 and 3 is 7, 3 and 4 is 7, 2 and 5 is 7, and 1 and 6 is 7. So there are 6 of those. That means that the rest of them are not 7s. So when you're doing odds, it's what you want compared to what you don't want. So we want 7s or don't want 7s, and the other thing are the non-7s. So if there are 36 things in the sample space and 6 of them are 7s, that means 30 of them are not 7s. And we're looking at the odds against 7, so we want the against number to be first. So it would be 30 to 6. If we wanted the odds in favor of a 7, it would be 6 to 30. Be sure to get that distinction. You don't want to get it backwards after doing all that hard work correctly. And you can reduce these odds by dividing both sides by 6 and get 5 to 1, by the way. How about a problem like this? A coin is tossed 3 times. What are the odds against the coin showing tails all 3 times? Before you can get into the details of computing the odds, you've got to figure out what the sample space is for this coin tossing experiment. One way you might do it is just to write out the sample space, and I would suggest that if you're going to do it that way, you'd use a tree diagram. Look at it this way. On the first toss of the coin, you could either get a head or a tail. On the second toss, if you got a head on the first toss, you could still get a head or a tail. If you got a tail on the first toss, you could either get a head or a tail. And continuing that pattern through the third toss, each succeeding toss would still have a possibility of head or tail. You can see from that, if you go down the branches of that tree diagram, that the sample space has 8 possibilities. You could do head, 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 tail, head, tail, head, head, tail, 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 head, head, tail, head, tail, 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 head, and tail, tail, tail. In other words, going down each branch vertically gives you one element of the sample space. So there are 8 members of that sample space. Now the question is about odds against the coin showing tails all 3 times. But if you look at your sample space, there's only one possible branch that gives you all tails. That's the tail, tail, tail branch. So there's one possibility, but there are 7 possibilities that don't give you all tails. So in terms of odds, you've got 7 against getting all tails and 1 in favor of getting all tails. So the odds against the coin showing all tails is 7 to 1. Now you might think drawing that sample space was sort of difficult because it takes up so much space. But think what would happen if you had more coin tosses, 4 or 5 or 6. It would get even worse. So it might be better to figure out a more efficient way to answer this question, because sometimes drawing the sample space is just not practical. So let's look at it this way. If I want to try to get those counts without really drawing that tree diagram, why not try the counting principle? Because it's just a series of choices, one after the other. In this case, with 3 coin tosses, it's a 3-stage process, and at each stage, I've got 2 choices: head or tail for the first toss, head or tail for the second toss, head or tail for the third toss. So by the counting principle, the number of ways to make the 3 tosses are 2 times 2 times 2, which will be 8. So there are 8 total ways, and you can see from that tree diagram that's exactly the same results we got. But the point is, I did not have to draw the tree diagram to get that result. And again, just as I did it earlier, only one of those possibilities is tail, tail, tail. The other 7 aren't, so you get the same result, that the odds against having all 3 tails is 7 to 1. I will say that using the counting principle for problems like this is especially useful when your coins go above 3. 3, practical to draw the tree diagram. But if you have more, suppose you had 6, it'd be really difficult to draw that tree diagram, drawing all those branches. And using the counting principle, you know that the total number of possibilities is 2 times 2 times 2 times 2 times 2 times 2, which is 2 to the 6, which is 64, because at each stage you still have two choices, head or tail, but you're doing it as a 6-stage process. So you're going to have, instead of 8 in the sample space, now you'll have 64 in the sample space, yet there's still only one that's all tails. That's tail, 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 tail. So the odds against the coin showing tails all 6 times will be 63 to 1. Going back to the previous problem with 3, it's 7 to 1. And again, there's only one that has all tails no matter how many coins you're tossing. The rest of them are not all tails. So the critical part of any of these problems is getting the 64 or the 8 or whatever that number is 2 to the power of how many coins you're going to toss. So you can see how that generalizes. You find the total number of possible tosses of n coins by taking 2 to the power of n. So in the 6th case, 2 to the 6th is 64. If you were tossing 5 coins, it'd be 2 to the 5th, it's 32. If you're doing 4 coins, it'd be 2 to the 4th, it's 16. That's a lot easier than trying to draw a tree diagram.